Light scattered like rumors in the schoolyard. Raman on the spectrum, never playing no trump card. Nobel in his grip like a vice is tight. Optics in his vision, physics taking flight. Lab coat tripping harder than the monsoon. Scattered light, he deciphered real soon. Might drop in the dark, shine bright, no gloom. India's own wizard worked in that room. Raman effect, twist reality, no mirage. Splitting light, making waves, causing barrage. Science in the blood, man was on a charge. Physicist with swagger, large and in charge. Spectroscopic jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Truth seeker, light breaker all day. Experimental flows busting through the gate. Royalty of science, Raman great. Pioneered the path, never played it safe. Physics in his palm, fate out the crate. Raman was the essence, no comma, pure finesse. Lab time grinding, no stopping, no recess. Light scatter tails under microscope stress. CV Raman physics, ultimate success.
We are surrounded by light. It bathes our world, a constant presence, yet its secrets remained hidden for centuries. Scientists, philosophers, they all pondered its nature, its essence. But it was an Indian scientist, a young man named Chandrasekhara Venkat Raman, who dared to look beyond the obvious, to question the very fabric of this everyday phenomenon. In a time of colonial rule, Raman, driven by an insatiable curiosity and a deep-seated belief in the power of Indian ingenuity, embarked on a journey of scientific exploration that would challenge the established order. He saw beyond the constraints imposed upon his nation, recognizing that true knowledge transcends borders and societal hierarchies. Raman, a master observer, was captivated by the myriad ways light interacted with the world around him. He saw the colors of the rainbow, the shimmering of a distant star, the way light refracted through a drop of water. These were not just beautiful sights, they were puzzles, invitations to delve deeper, to unravel the mysteries concealed within this seemingly simple phenomenon. This is the story of C.V. Raman, a visionary who, through a simple yet profound experiment, unlocked the secrets of light scattering, a discovery that would not only revolutionize our understanding of the universe but also inspire generations of scientists across the globe. Join us as we delve into the life and work of this extraordinary individual, whose legacy continues to illuminate the path of scientific progress.
A very powerful radio telescope is being installed by the Raman Research Institute at Bangalore. If there is a God, we must look for him in the universe. If he is not there, he is not worth looking for, said the founder of the institute, Chandrasekhar Venkat Raman.
C.V. Raman, driven by an insatiable curiosity, embarked on a series of ingenious experiments, a series of castle systems if you will, to unlock the hidden secrets of light. These castle systems, as we might call them, were elaborate setups of lenses, prisms, and filters, each piece carefully chosen and precisely aligned. Raman, a master of experimental design, constructed these intricate apparatuses to meticulously study the behavior of light as it interacted with various substances. He observed light as it passed through liquids, solids, and gases, noting the subtle shifts in its wavelength and intensity. These meticulous observations, conducted with unwavering patience and unwavering dedication, led him to a groundbreaking discovery. Raman discovered that when light interacts with matter, it undergoes a subtle shift in frequency, a phenomenon he termed the Raman effect. This seemingly minor shift, invisible to the naked eye, revealed profound truths about the molecular structure of matter. The castle systems that Raman so meticulously constructed became the foundation for a new era of scientific exploration. The Raman effect has since become an invaluable tool across various fields, from medicine and materials science to art conservation and even astrophysics.
My life has been an utter failure. I was the first Asian to bring home the Nobel Prize in the scientific field.
He was one of India's greatest physicists, the acknowledged leader of the early scientific movement in this country. Nobel laureate, he is renowned for a discovery that bears his name, the Raman effect. Why then, in the twilight of his life, does he look back not with pride and satisfaction? The young Raman was curious by nature. He wanted to know more about everything that he saw and heard. For the rest of his life, this curiosity, combined with an inherent love for nature, drove him to study her many facets.
C.V. Raman's first major work delved into the intricate world of diffraction of light. This phenomenon occurs when light waves encounter an obstacle or an opening, causing them to bend and spread. Think of it like water waves encountering a barrier in a pond. The waves don't simply stop, they bend around the obstacle, creating a pattern of ripples. Similarly, when light passes through a narrow slit or around the edge of an object, it doesn't travel in a straight line but bends and spreads out. Raman meticulously studied this diffraction phenomenon, conducting experiments and analyzing the patterns formed when light interacted with various objects. His research led to valuable insights into the behavior of light waves and their interactions with matter. This early work, published in the prestigious Philosophical magazine in 1906, showcased Raman's keen intellect and his dedication to scientific inquiry. It laid the foundation for his future groundbreaking research, ultimately leading to the discovery of the Raman effect, which earned him the Nobel Prize in Physics. Following his pioneering work on the diffraction of light, C.V. Raman embarked on a fascinating journey into the realm of acoustics, specifically the intricate physics of musical instruments. This period saw him delve deeply into the captivating world of sound, exploring the vibrational properties of various instruments with a meticulousness that mirrored his approach to light. Raman's interest in music wasn't merely a casual diversion, it was a deeply ingrained passion. He saw in musical instruments not just objects of artistic expression, but intricate systems governed by fundamental laws of physics. He meticulously examined the violin, its strings vibrating in intricate patterns, the resonance of its wooden body amplifying the sound. He delved into the subtleties of Indian percussion instruments, such as the mridangam and the tabla, analyzing how the tension of the membranes, the shape of the drums, and the precise techniques of the musicians contributed to the unique timbres and rhythmic complexities. Raman's approach was multifaceted. He wasn't content with merely observing, he sought to understand the underlying principles. He meticulously measured vibrations, analyzed sound waves, and explored the interplay between the instrument's physical properties and the musician's artistry. He dissected the intricate dance of resonance, the way vibrations within the instrument interact and amplify to produce the rich tapestry of sounds that we perceive. This period of research yielded significant insights into the physics of sound. Raman's investigations into the vibrational modes of musical instruments provided valuable data on resonance, wave propagation, and the complex interplay between structure and sound. His work not only deepened our understanding of acoustics but also demonstrated his remarkable ability to bridge seemingly disparate fields, physics and music, demonstrating the interconnectedness of knowledge and the power of interdisciplinary inquiry. Beyond the purely scientific contributions, Raman's exploration of musical acoustics highlights his deep appreciation for art and culture. He saw in music not just a form of entertainment, but a profound expression of human creativity and a reflection of the underlying principles that govern the natural world. This holistic approach, encompassing both scientific rigor and an appreciation for artistic expression, became a hallmark of Raman's intellectual pursuits throughout his illustrious career. C.V. Raman's pioneering research delved into the physics of sound, particularly in the context of musical instruments. Building upon his foundational work, contemporary researchers are exploring innovative avenues that blend traditional instrument making with cutting-edge technologies. One prominent area is computational acoustics and instrument design. This involves leveraging the power of artificial intelligence to revolutionize how instruments are conceived and crafted. By feeding vast datasets of instrument designs, playing styles, and the resulting sounds into sophisticated machine learning algorithms, researchers can gain invaluable insights. This data-driven approach allows for the creation of novel instruments with precisely optimized acoustics. These instruments can be tailored to specific musical genres, individual player preferences, or even to address unique performance challenges. Furthermore, the concept of digital twin instruments is gaining significant traction. This involves creating highly accurate digital replicas of real-world instruments. These virtual counterparts serve multiple critical purposes. Firstly, they enable predictive maintenance. By continuously monitoring the digital twin, potential issues within the physical instrument can be identified and addressed proactively, minimizing downtime and costly repairs. Secondly, digital twin instruments facilitate virtual prototyping. Designers can experiment with various design modifications and their acoustic implications within the virtual environment. This eliminates the need for costly and time-consuming physical prototypes, accelerating the design and development process. In essence, these modern approaches, inspired by C.V. Raman's foundational work, are poised to transform the landscape of musical instrument design and performance. By integrating AI and advanced computational techniques, researchers are pushing the boundaries of what's possible in musical acoustics, leading to the creation of innovative and inspiring instruments that enrich the musical experience for both players and audiences alike.
C.V. Raman was born at Tiruvannaikkaval near Tiruchirappalli in Tamil Nadu on 7th November 1888 to Parvati Ammal. Chandrasekhar Iyer, his father, was a school teacher.
Even at the age of 82, he was exploring new vistas as actively as he did as a child. For him, science had always been the key to understanding the workings of the world around him.
Raman was the second of 8 children.
Fascinated, he mastered such classics as Ganot's physics. There is a story that late one night, despite high fever, he refused to sleep till his father, a science lecturer, fetched a Leyden jar from his college and showed him how it worked.
The Raman effect, a cornerstone of modern spectroscopy, can be described linguistically as a subtle conversation between light and matter. Imagine a beam of light, composed of tiny particles called photons, encountering a molecule. Most often, the photon simply bounces off, much like a tennis ball hitting a wall. This is called Rayleigh scattering. However, in a less frequent but crucial interaction, the photon exchanges energy with the molecule. This energy exchange can be likened to a brief discussion where the photon either gives a little energy to the molecule, making it vibrate more intensely, or receives a bit of energy from the molecule, causing the photon to slow down. This subtle energy transfer, though seemingly insignificant, leaves a unique fingerprint on the scattered light. By analyzing the shifts in the light's energy or frequency, scientists can decipher the vibrational language of the molecule, revealing its structure and composition. The Raman effect, therefore, provides a powerful tool for listening to the inner workings of molecules, much like eavesdropping on a conversation to understand the nuances of a relationship. This ability to converse with matter at the molecular level has profound implications for fields ranging from chemistry and materials science to medicine and environmental monitoring. The Raman effect, a profound concept in physics and spectroscopy, can be further explained through a more nuanced linguistic lens. Imagine a beam of light, a cascade of photons, encountering a molecule. This encounter is not always a simple bounce off like a billiard ball striking another. Instead, it's a more intricate interaction, a subtle dialogue where energy is exchanged. This exchange can be visualized as a fleeting impartation or absorption of energy. The photon, carrying its own energy, can impart some of it to the molecule, causing the molecule's internal vibrations to intensify. Conversely, the photon can absorb energy from the molecule, reducing its own energy content. This seemingly minor energy exchange, this brief give and take between light and matter, leaves an indelible signature on the scattered light. The shift in the light's energy, its frequency, becomes a unique fingerprint of the molecule. By meticulously analyzing these subtle shifts, scientists can decipher the vibrational language of the molecule. This language reveals intricate details about the molecule's structure, the arrangement of its atoms, and the nature of the chemical bonds that hold it together. The Raman effect, therefore, provides a powerful tool for deciphering the molecular world. It allows scientists to listen to the intricate conversations happening within molecules, to understand their vibrational rhythms and melodies. This ability to converse with matter at the molecular level has far-reaching implications, impacting fields like chemistry, materials science, medicine, and environmental monitoring. By employing Raman spectroscopy, scientists can identify unknown substances, analyze the composition of complex materials, diagnose diseases, and even monitor environmental pollutants. This profound understanding of the molecular world, gleaned through the subtle dialogues revealed by the Raman effect, continues to push the boundaries of scientific discovery. The discovery of the Raman effect in 1928 by C.V. Raman and K.S. Krishnan marked a significant turning point in our understanding of light-matter interactions. This groundbreaking discovery paved the way for numerous advancements in spectroscopy and its applications across various scientific disciplines. The invention of the laser in the 1960s revolutionized Raman spectroscopy. The laser's intense, monochromatic light significantly enhanced the sensitivity and efficiency of Raman measurements. This technological breakthrough revived Raman spectroscopy, transforming it from a niche technique to a powerful analytical tool. The development of surface-enhanced Raman spectroscopy SIRS techniques, such as those involving metallic nanoparticles, dramatically amplified the Raman signal, making it possible to detect even minute quantities of molecules. This has opened up new avenues for applications in fields like chemical sensing, biomedicine, and environmental monitoring. Continuous advancements in instrumentation, including the development of high-resolution spectrometers, improved detectors, and fiber optic probes, have further enhanced the capabilities of Raman spectroscopy. These technological advancements have made Raman spectroscopy more accessible, robust, and adaptable to a wide range of applications. The Raman effect has found applications in a diverse array of fields, including chemistry, where it is used to identify and characterize chemical compounds, study chemical reactions, and analyze molecular structures. In materials science, it investigates the properties of materials, such as polymers, ceramics, and semiconductors. In biomedicine, it is employed in diagnosing diseases, monitoring drug delivery, and studying biological processes at the molecular level. In environmental science, it is used to detect and monitor pollutants, analyze environmental samples, and study ecological systems. Additionally, it plays a crucial role in forensic science, aiding in the analysis of evidence, such as fibers, paints, and explosives. Researchers continue to explore and develop new Raman spectroscopy techniques, such as tip-enhanced Raman spectroscopy (TERS), which combines Raman spectroscopy with atomic force microscopy to obtain nanoscale spatial resolution. Spatially offset Raman spectroscopy (SORS) enables non-invasive analysis of samples through opaque layers. Resonance Raman spectroscopy provides enhanced sensitivity for specific molecules by tuning the laser excitation wavelength to match electronic transitions within the molecule. These advancements demonstrate the enduring legacy of the Raman effect. From its initial discovery to the cutting-edge techniques of today, Raman spectroscopy continues to play a vital role in advancing scientific knowledge and addressing critical challenges in various fields.
This is the horoscope of Raman. But Raman did not believe in astrology. When Raman was just 3 years old, his father became a lecturer in the Avian College at Visakhapatnam.
See, a large amount of charge is accumulated at the bottom. You connect this to the electrode, it gets discharged.
Apriya, there's a spark.
This is where they lived. While listening to his father's violin, the young Raman perhaps looked at the roaring sea and wondered, why is the sea blue? Why is the sky blue? The seeds of his future discovery were probably sown during these days of sea and sky watching.
Raman was born near Tiruchirappalli in Tamil Nadu in 1888. From there the family moved to the coastal town of Visakhapatnam when he was 4 years old. The sun, the sea, nature in all its primordial beauty here must have first stirred the young boy.
The terms Raman effect and Raman scattering are often used interchangeably, but they represent distinct linguistic concepts. The Raman effect refers to the broader phenomenon of inelastic scattering of light by matter, encompassing the observation and interpretation of the energy shifts that occur in the scattered light. It serves as the overarching concept and the scientific principle underlying this interaction. In contrast, Raman scattering specifically describes the process where light interacts with a molecule, inducing molecular vibrations. During this interaction, the scattered light can either gain or lose energy, resulting in a shift in its frequency. This term focuses on the actual physical process of light scattering with energy exchange. In simpler terms, the Raman effect can be considered the overarching linguistic concept, encompassing the entire observation and its implications. Conversely, Raman scattering represents the specific linguistic term denoting the underlying physical process that gives rise to this observed phenomenon. The analysis presented provides a foundational understanding of the linguistic distinctions between these two terms. However, there are several avenues for further exploration. A deeper linguistic analysis could involve examining the etymology and historical development of the terms Raman effect and Raman scattering. How have their meanings evolved over time within the scientific community? Additionally, an investigation into the grammatical and semantic relationships between these terms and other related concepts in physics and spectroscopy could provide valuable insights. Furthermore, analyzing the use of these terms in different scientific contexts and by different communities of scientists would offer a broader perspective on their usage and interpretation. Expanding the scope of the analysis beyond the purely linguistic could prove fruitful. Considering the broader linguistic implications of the Raman effect and its applications is crucial. How does the language used to describe this phenomenon shape our understanding of light, matter, and the universe? Exploring the role of language in the communication and dissemination of scientific knowledge related to the Raman effect would shed light on how language influences scientific discourse and public understanding. Finally, this linguistic analysis can have practical applications. Utilizing these insights to improve scientific communication and education is essential. Creating more precise and effective definitions and explanations of the Raman effect and Raman scattering for different audiences, including students, researchers, and the general public, would enhance clarity and understanding. Developing new pedagogical approaches that leverage the insights gained from this linguistic analysis could significantly improve the teaching and learning of these concepts in educational settings. By further exploring these avenues, we can gain a deeper and more nuanced understanding of the linguistic dimensions of the Raman effect and its significance in the broader context of scientific discourse. This comprehensive understanding can not only enhance scientific communication but also contribute to a more profound appreciation of the interplay between language and scientific knowledge. Following the significant advancements in Raman spectroscopy techniques and their expanding applications, a crucial area of progress lies in the development and application of sophisticated machine learning and data analysis methods. Traditional methods for analyzing Raman spectra often involve manual interpretation and comparison with spectral libraries, which can be time-consuming, subjective, and prone to human error. However, the increasing volume and complexity of Raman spectroscopic data necessitate the adoption of more robust and efficient analytical approaches. Machine learning algorithms offer powerful tools for extracting meaningful information from Raman spectra. These algorithms can be trained on large datasets of spectra to identify patterns, classify samples, and make predictions with high accuracy. Some of the key machine learning techniques employed in Raman spectroscopy include supervised learning. Algorithms such as support vector machines (SVM), random forests, and artificial neural networks (ANNs) can be trained on labeled datasets to classify samples based on their spectral characteristics. This is particularly useful for applications such as disease diagnosis, material identification, and quality control. Unsupervised learning. Techniques like principal component analysis (PCA) and k-means clustering can be used to identify inherent patterns and group similar spectra together, even in the absence of prior labels. This is valuable for exploratory data analysis and identifying unknown substances. Deep learning. Deep neural networks, such as convolutional neural networks (CNNs) and recurrent neural networks (RNNs), have shown remarkable success in analyzing complex data, including images and time series. These models can effectively extract high-level features from Raman spectra, leading to improved classification accuracy and enhanced understanding of molecular interactions. Furthermore, advancements in data analysis techniques, such as multivariate curve resolution (MCR) and chemometrics, enable the deconvolution of complex spectra, identification of overlapping spectral components, and quantification of individual species within a mixture. The integration of machine learning and data analysis with Raman spectroscopy is revolutionizing its applications in various fields. These advancements not only improve the accuracy and efficiency of data analysis but also enable the discovery of new insights and the development of novel applications in areas such as precision medicine, early and accurate diagnosis of diseases, personalized treatment plans, and monitoring of disease progression. Pharmaceutical research, drug discovery, quality control, and analysis of drug-target interactions. Food safety and quality, detection of contaminants, adulteration, and spoilage in food products. Environmental monitoring, identification and quantification of pollutants, assessment of environmental impact, and monitoring of ecological systems. Materials science, characterization of materials, quality control, and development of new materials with tailored properties. In conclusion, the combination of advanced Raman spectroscopy techniques with cutting-edge machine learning and data analysis methods is driving significant advancements in scientific research and technological innovation. By leveraging the power of these tools, scientists can unlock new insights into the molecular world and address critical challenges in various fields, from healthcare and pharmaceuticals to environmental science and materials engineering. This continuation expands on the previous discussion by focusing on the crucial role of machine learning and data analysis in modern Raman spectroscopy. It highlights the limitations of traditional methods and emphasizes the advantages of employing sophisticated algorithms for analyzing complex spectral data.
At the rather tender age of 13, Raman joined the Presidency College Madras. Some of his teachers originally thought that he was a schoolboy who entered the college by mistake.
He began to ask questions. His father encouraged his curiosity. As Raman's thirst for knowledge grew, he was spurred to take science up seriously in later years.
The same teachers later praised his caliber profusely. In fact, they exempted him from attending the science classes because he was far ahead of his class. His first research paper, unsymmetrical diffraction bands due to a rectangular aperture.
Sir, I'm trying to work out a new method of measuring the surface tension of liquids. New method? Why? Because by the usual method, either the drop is not steady or it falls down in the middle of the observation.
Raman worked with the association in the mornings before going to his office, and again in the evenings. On Sundays and holidays, he worked the whole day. Within a few years, he published a number of research papers on physics.
So I thought if I could photograph the drop profile, it would be easier to calculate the surface tension.
Sounds ingenious. Carry on.
Oh, sir, Professor Jones, sir. One moment, please.
Yes?
Some time ago, I'd given you a paper of mine for comments.
A paper?
The Raman effect describes the inelastic scattering of light by matter, meaning that both energy and the direction of the light change during the interaction. When a beam of light interacts with a molecule, most photons are scattered elastically, rarely scattering, retaining their original energy and frequency. However, a small fraction of these photons undergo inelastic scattering, exchanging energy with the molecule. This energy exchange results in a shift in the frequency of the scattered light, a phenomenon known as the Raman shift. The Raman shift provides valuable information about the vibrational energy levels of the molecule. If the molecule gains energy from the incident photon, the scattered light will have a lower frequency, longer wavelength, known as Stokes-Raman scattering. Conversely, if the molecule loses energy to the incident photon, the scattered light will have a higher frequency, shorter wavelength, known as anti-Stokes-Raman scattering. The intensity of Raman scattering is related to the polarizability of the molecule, which is a measure of how easily the electron cloud of the molecule can be distorted by an external electric field. The interaction between the incident light's electric field and the molecule's polarizability induces a dipole moment in the molecule, leading to the scattering of light. A rigorous theoretical description of the Raman effect requires quantum mechanics. The interaction between the incident light and the quantized vibrational states of the molecule involves complex calculations using time-dependent perturbation theory to determine the probabilities of transitions between different vibrational levels. The Raman effect has significant scientific and technological applications. Raman spectroscopy, which utilizes the Raman effect to analyze materials, is widely employed in various fields, including chemistry, materials science, biology, and medicine. By analyzing the Raman spectra of substances, researchers can obtain valuable information about their molecular structure, composition, and properties. Disclaimer: this explanation provides a simplified overview. The actual mathematical treatment of the Raman effect is quite complex and involves advanced quantum mechanics and electromagnetic theory. The Raman effect, at its core, stems from the interaction between light and the vibrational energy levels of a molecule. At the fundamental level, the Raman effect is a quantum mechanical phenomenon. When a photon interacts with a molecule, it can induce transitions between different vibrational energy levels within the molecule. A key concept is the molecular polarizability tensor, a second-rank tensor that describes how the electron distribution within a molecule is distorted by an external electric field. This distortion, in turn, influences the molecule's interaction with light. Molecules possess distinct vibrational modes, each with a characteristic frequency. Raman scattering probes these vibrational modes by revealing the energy differences between the ground vibrational state and excited vibrational states. Not all vibrational modes are Raman active. The Raman scattering intensity depends on the symmetry properties of the vibrational mode and the polarizability tensor. These rules, known as selection rules, dictate which vibrational modes are allowed to undergo Raman scattering and are derived from group theory, depending on the symmetry of the molecule and the vibrational mode. If the energy of the incident light matches an electronic transition within the molecule, a significant enhancement of the Raman scattering intensity can occur. This phenomenon is known as resonance Raman scattering and provides significantly higher sensitivity for specific molecules, making it a powerful tool for studying chromophores molecules that absorb light and biological systems. A rigorous theoretical description of the Raman effect involves time-dependent perturbation theory, which allows for the calculation of transition probabilities between different vibrational states of the molecule under the influence of the incident light. Modern computational methods, such as density functional theory (DFT), are employed to calculate molecular polarizabilities and predict Raman spectra with high accuracy. The development of integrated Raman spectroscopy for non-destructive analysis represents a significant advancement in analytical techniques. The primary motivation is the need for analytical methods that do not damage or alter the sample being investigated. This is crucial in various fields, such as art conservation, where analyzing ancient artifacts without causing damage is paramount. In the pharmaceutical industry, assessing drug quality and stability without compromising the medication's integrity is essential. Similarly, in materials science, characterizing materials without affecting their structural or functional properties is crucial. In the food industry, detecting contaminants or adulterants in food products without altering their composition is vital for ensuring food safety. Integrating Raman spectroscopy into various systems and platforms is crucial for real-world applications. This involves miniaturizing Raman spectrometers to create compact and portable devices for field use. Automating sample handling and data analysis is essential for high-throughput applications. Furthermore, combining Raman spectroscopy with other analytical techniques, such as microscopy, imaging, and robotics, enhances its capabilities. Key advancements in this field include the development of miniaturized Raman spectrometers using microelectromechanical systems MEMS and fiber optics, enabling the creation of compact and portable devices. Advancements in laser technology, detectors, and data analysis algorithms have significantly improved the sensitivity and specificity of Raman spectroscopy, allowing for the detection of smaller amounts of analytes and the differentiation of complex mixtures. Surface-enhanced Raman spectroscopy SIRS, utilizing metallic nanostructures, dramatically amplifies the Raman signal, enabling the detection of even minute quantities of molecules. Combining Raman spectroscopy with microscopy techniques, such as confocal microscopy and atomic force microscopy, allows for spatially resolved chemical analysis, enabling the mapping of chemical composition and identifying variations within a sample. Chemometric methods, such as multivariate curve resolution and machine learning algorithms, are used to extract meaningful information from complex Raman spectra, enabling the identification of unknown substances, the quantification of analytes, and the prediction of material properties. The applications of integrated Raman spectroscopy are widespread. In art conservation, it is used to analyze pigments, identify materials, and assess the condition of artworks without causing damage. In the pharmaceutical industry, it monitors drug quality, detects impurities, and analyzes drug delivery systems. In food safety, it detects foodborne pathogens, identifies adulterants, and assesses the freshness of food products. In materials science, it characterizes materials, identifies defects, and assesses the quality of manufactured goods. In environmental monitoring, it detects pollutants, analyzes environmental samples, and studies ecological systems. In biomedical applications, it diagnoses diseases, monitors drug delivery, and studies biological processes at the molecular level.
Deeply struck by the blue color of the Mediterranean, he began his research and later proved that the blueness of the sea is not due to the reflection of the sky, but due to the scattering of light by water. Then came the famous experiments.
Yes, on unsymmetrical diffraction bands when the incident light is oblique.
Really? Ah, yes. Perhaps you did. Well, it is nothing much to go by. Nothing at all. Carry on with your work.
That culminated in the discovery of a new radiation. Surprisingly, the experiment was carried out with simple instruments, which cost a mere 200 rupees.
What is research? It is only seeking after knowledge. Knowledge is not dead and enshrined in books, but living, growing. It is the attempt to discover new facts and new relationships between known facts. A university is not a university if this is not understood. You must be one of the seekers, else you'll be left behind.
Way back in 1907, a handful of Indians were still struggling to create a niche for themselves in areas dominated by the British.
On 29th February 1928, the announcement of the discovery was made. The whole world took note of this exciting discovery when Raman published it in the prestigious journal Nature.
There was no scope for a scientific career, as there is now in post-independent India. So Raman decided to do the next best thing, join the government. Topping the entrance examination to the Financial Civil Service, he was appointed Assistant Accountant General.
What is this new radiation? When light collides with molecules of matter, it mostly loses energy, but sometimes gains energy from the molecules and comes out with a higher energy. This is the new radiation, or the Raman effect.
I will write it down. C. Venkatraman. I'm a government servant. The Assistant Accountant General, in fact. But I'm interested in continuing to do my research in my spare time. Original investigation in optics and acoustics.
Well, come with me.
The thick lines are the incident radiation. The thin lines are the Raman lines, his discovery. The Raman radiation principle of excess energy can be explained thus.
Oh, there's so much that can be done. You know something? Max Born is coming.
Sir, have you heard from him?
Yes, I've received his letter this morning. He's accepted the readership I offered him. Just wait and see, my friend. Things will begin to change for India.
For this discovery, Raman was awarded the most coveted Nobel Prize for Physics on December 11, 1930.
The concept of wave numbers in Raman spectroscopy transcends mere units. It serves as a fundamental link between the observed spectral features and the underlying molecular vibrations. Raman shifts, the energy differences between the incident and scattered photons, are conventionally expressed in units of wave numbers cm1. This unit, representing the number of waves per centimeter, provides a convenient and directly interpretable energy scale. Each Raman peak corresponds to a specific vibrational mode within the molecule, and its position in the wave number spectrum directly reflects the energy of that vibrational transition. Beyond simply representing energy, wave numbers carry crucial information about the molecular structure and dynamics. By analyzing the positions and intensities of Raman peaks, researchers can identify specific functional groups, characteristic vibrational frequencies for various functional groups, e.g. CH, C equals O, CC are well established in Raman spectroscopy. By comparing observed Raman shifts to known databases, researchers can identify the presence of specific functional groups within a molecule. Determine molecular symmetry. The selection rules governing Raman activity are intimately linked to the symmetry of the molecule and its vibrational modes. Analyzing the presence or absence of certain Raman peaks provides valuable insights into the molecular symmetry. Investigate molecular interactions. Changes in the positions and intensities of Raman peaks can reveal information about intermolecular interactions, such as hydrogen bonding and van der Waals forces. Monitor chemical reactions. Raman spectroscopy can be used to monitor the progress of chemical reactions by observing changes in the Raman spectra of reactants and products. Furthermore, advancements in computational chemistry enable the theoretical calculation of Raman spectra, providing a powerful tool for interpreting experimental data and assigning specific vibrational modes to observed peaks. These calculations often involve predicting the frequencies of vibrational modes and comparing them to experimentally observed Raman shifts. In essence, wave numbers in Raman spectroscopy are more than just units. they represent a crucial link between the observed spectral features and the underlying molecular structure and dynamics. By carefully analyzing the positions and intensities of Raman peaks in the wave number domain, researchers can gain profound insights into the molecular world. Multivariate analysis techniques, such as principal component analysis (PCA) and partial least squares (PLS), are invaluable for extracting meaningful information from the complex data generated by Raman spectroscopy, particularly when analyzing mixtures or intricate biological systems. These methods effectively address the challenges posed by overlapping spectral peaks and subtle variations within the data. PCA and PLS act as powerful organizational tools, transforming the high-dimensional spectral data into a more manageable set of principal components or latent variables. This process not only reduces noise and simplifies the data but also preserves the most crucial information. By focusing on these key components, these techniques can effectively separate signals originating from different components within a mixture, even when their spectral signatures overlap. Furthermore, multivariate analysis excels at identifying subtle spectral variations that might easily be overlooked in conventional analysis. These subtle variations can hold critical information for applications such as disease diagnosis or quality control. By emphasizing the most relevant spectral features, multivariate analysis enhances the sensitivity and specificity of Raman analysis, leading to more reliable detection and quantification of analytes. In essence, multivariate analysis empowers researchers to navigate the complexities of Raman spectra, enabling them to extract valuable insights and make more informed interpretations. It's akin to organizing a cluttered room, grouping similar items, discarding unnecessary clutter, and highlighting the most important features. This organized approach facilitates easier navigation and a deeper understanding of the overall structure within the data. Quantum plasmonics represents a cutting-edge frontier in Raman spectroscopy, where the field merges with the study of how light interacts with metallic nanostructures. Plasmonics, in essence, explores the behavior of light confined and manipulated at the nanoscale within these structures. Quantum plasmonics extends this concept further, delving into the realm where the collective oscillations of electrons within the metal, known as plasmons, exhibit quantum behavior. This integration significantly advances Raman spectroscopy in several ways. By incorporating plasmonic nanostructures into techniques like surface-enhanced Raman spectroscopy (SERS), researchers can achieve dramatic enhancements in the Raman signal. This breakthrough enables the detection of minuscule amounts of molecules, even down to the level of single molecules, which was previously unattainable. Furthermore, quantum plasmonic structures provide unprecedented control over the interaction between light and the molecules under investigation. This control allows for the precise manipulation of the Raman scattering process itself. Researchers can now direct and focus Raman signals, control the spectral properties of the scattered light, and achieve higher levels of sensitivity and spatial resolution. The implications of quantum plasmonics are far-reaching. In the realm of biosensing, it enables the ultra-sensitive detection of biomolecules such as proteins, DNA, and viruses, revolutionizing medical diagnostics and environmental monitoring. In materials science, it provides powerful tools for characterizing and understanding the properties of novel materials at the nanoscale. Moreover, quantum plasmonics holds immense potential for the development of advanced quantum technologies, such as quantum sensors and quantum computers, by leveraging the unique interactions between light and quantum plasmonic systems. Beyond quantum plasmonics, other exciting advancements are pushing the boundaries of Raman spectroscopy. Nonlinear Raman spectroscopy techniques, such as coherent anti-Stokes Raman scattering CARS and stimulated Raman scattering SRS, offer improved sensitivity and spatial resolution. Tip-enhanced Raman spectroscopy TERS, which combines Raman spectroscopy with atomic force microscopy, achieves sub-nanometer spatial resolution, providing unprecedented detail in imaging and analysis. Additionally, the utilization of novel light sources, including ultrafast lasers and supercontinuum lasers, is exploring new frontiers in Raman scattering, expanding the capabilities of this powerful analytical technique. These ongoing advancements in Raman spectroscopy are constantly pushing the boundaries of scientific discovery, leading to new insights and applications across a wide spectrum of fields.
Innumerable awards were to follow: the Hughes Medal, the Franklin Medal, and many others, including the highest national award, the Bharat Ratna.
I propose this evening to speak to you on a new kind of radiation, or light emission, from atoms and molecules. To make the significance of the discovery clear, I propose to place before you the history of the investigations made at Calcutta which led up to it. In 1923, it was K.R. Ramanathan who noticed the strange phenomenon while he was studying the scattering of light in liquids.
The Raman effect opened up a new method to understand the structure of complex organic molecules. The discovery and developments of a lot of synthetic fibers, medicines, paints, and a host of other materials have been accelerated by the Raman effect. And all his work was initiated and carried out
Professor Raman,
in India. He was invited to a number of countries to give talks on his discovery.
this green filter, it's complementary to the violet, so it cuts off all the violet color passing through. But when I place it here, in the path of the scattered light, the result is not the same. There's a track of light visible.
A track of light, in spite of a complementary filter.
Within a decade of its discovery, more than 1,000 research papers were published on the Raman effect throughout the world, many of them by his own students.
Depends upon the point of view that you take. For example, if we ask ourselves, who was the first person who observed the Raman effect? There is no doubt that the first visual observation through a direct vision spectroscope was made by Raman himself.
November 21st, 1970. A true colossus fades away into history. Professor C.V. Raman is no more. But his original research in physics and his dedication to science will continue to inspire generations of scientists from all parts of the world.
Light scattered like rumors in the schoolyard. Raman on the spectrum, never playing no trump card. Nobel in his grip like a vice is tight. Optics in his vision, physics taking flight. Lab coat dripping harder than the monsoon. Scattered light he deciphered real soon. Light dropped in the dark, shine bright, no gloom. India's own wizard worked in that room. Raman effect, twist reality, no mirage. Splitting light, making waves, causing barrage. Science in the blood, man was on a charge. Physicist was swagger large and in charge. Spectroscopy jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Truth seeker, light breaker all day. Experimental flows busting through the gate. Royalty of science flaming great. Pioneered the path, never played it safe. Physics in his palm, fate out the crate. Ramen was the essence, no comma, pure finesse. Lab time grinding, no stopping, no recess. Light scattered tales under microscope stress. CV rhyming physics, ultimate success. Dripping harder than the monsoon. Scattered light, he deciphered real soon. A mic drop in the dark, shine bright, no gloom. India's own wizard worked in that room. Ramen effect, twist reality, no mirage. Splitting light, making waves, causing barrage. Science in the blood, man was on a charge. Physicist with swagger, large and in charge. Spectroscopy jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Physicist with swagger, large and in charge. Spectroscopy jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Physicist with swagger, large and in charge. Spectroscopy jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Truth seeker, light breaker all day. Spectroscopy jive, he's the maestro at play. Atoms dancing in the light like cabaret. Wavelength shift, catch it on display. Truth seeker, light breaker all day. Experimental flows busting through the gate. Royalty of science reigning great. Pioneered the path, never played it safe. Physics in his palm, fate out the crate. Ramen was the essence, no comma, pure finesse. Lab time grinding, no stopping, no recess. Light scattered tales under microscope stress. CV rhyming physics, ultimate success.